In this section, we're going to study quadratic functions. And some of this will be review because you've done work with quadratic functions, most likely, or you should have, in your intermediate algebra course or whatever equivalent course you had. And we've also been working with them in the transformation section when we graph the parabolas, the y equals x squared function. When we transform that, those are quadratics. All right, well, in the notes here, start with just a more general function, the polynomial function, which here's our definition. It says it's a function of this form. Looks kind of long and complicated, but it's really not. We just have coefficients on our x terms and then powers on each of these x's, and the way this is written, you know, if this n is a 5, then the next term is 5 minus 1 is a 4, n minus 2 would be 3, etc., until you get down to x to the first, and then this doesn't have an x term in it, but you could put x to the 0 there, and of course x to the 0 equals 1. So each of these terms has a degree associated to it. This is degree n, this is degree n minus 1, n minus 2, etc. This is first degree term, and this is the, this would be considered to have degree 0. I should have pointed out these n's, the n in this is a whole number. So, we can't have like a 1/2 here. If that's a 1/2, then this isn't a polynomial. And likewise, it can't be a negative integer. So -5 would make this not a polynomial. We're going to actually talk more about that in the next section, so I don't want to spend too much time on that. I just wanted to point out the definition and then make note that we've already worked with some of these. The polynomials of degree 0 are constant functions, and we talked about constant functions back in the section where we looked at all the basic elementary functions, right? And we said those all are horizontal lines when you graph them. Then a polynomial of degree 1 would be a linear function. This would be up here would be a sub 1x plus a sub 0, but these numbers here would really be our slope and intercept, so we'll change to m and b when we write that. And of course, these, when graphed, would not be horizontal lines and they would not be vertical lines. If we have an x, then it's not horizontal. And then polynomial functions of degree 2, these are our quadratic functions, and that's what we're going to study today. I have the formal definition down here. And of course, I already mentioned we already worked with some of these. So let's look at the definition. A quadratic function is a function that can be written in the form ax squared plus bx plus c. So y equals that, or f at x equals that if you're using function notation. And a can't be 0, because if a is 0, then you don't have the x squared term. So the x squared term is what, of course, makes it quadratic. This is referred to as the general form of the quadratic. And that reminds me, I should point out with a polynomial, this is called the standard form. Almost forgot to mention that. Standard form of a polynomial means the powers are in descending order. Okay, so every quadratic function, when you graph it, you always get a parabola. And a parabola has symmetry through the vertex. Now, because these are functions, the quadratic function, the parabola must either open up or it could possibly open down, right? But it won't open to the side. It's still a parabola if it does, but it's not a quadratic function because it would fail the vertical line test. So this line through the vertex where we have the symmetry is called the axis of symmetry. And sometimes it's just referred to as the axis. So you can drop the of symmetry part of it. And of course, this one would be here. If the parabola opens upward, then we have a minimum at the vertex. That's the minimum function value. Of course, the lowest point on the graph. And if it opens, and that's going to be the function value is the y-coordinate. Right? When you plug in your x, you get the output. That's the min. This one would have a maximum happening here. And of course, that would be whatever this y-coordinate is. Let's see, what else? Well, there's more, but we'll deal with it as we go here. So let's look at the next page. Okay, and we've talked about our most basic function, y equals x squared, or f at x equals x squared. My graph didn't all the way show up here. I don't know why the printer does that sometimes. All right, so when you're graphing the y equals x squared, it's really helpful to remember this basic form that if you're going from the center or the axis of symmetry, when you're graphing, or I should say from the vertex when you're graphing, that the basic form, when you go out 1, you go up 1 in both directions, and when you go out 2, then you're up 4. That will help you when you do stretches to remember that, okay? Well, actually, even if it's not stretched or compressed, just to remember from the vertex, you go out 1, up 1, and then out 2, up 4. Of course, that has to be adjusted if there's a stretch or compression. And if it opens downward, it's out 1, down 1, out 2, down 4. We don't want to do point plotting, of course. We want to use what we know. So remember that pattern. Okay, well, we talked about the transformations, and with the transformations, we get this form, which looks different, of course, than this form. But we can go back and forth between the two forms. Here's an example. If we square this, we'll get an x squared term and an x term, and we can write it in ax squared plus bx plus c form. I won't do that here, but you know that could easily be done with algebra. If it is in this form, we know from our transformations that we know if h is positive, we're going to move to the left, and if h is negative, well, I shouldn't say, if h is negative, this actually becomes a positive, and we move to the left. And if h is positive, then we're subtracting a positive. We move to the right. So this is, as that's shifting, that's where the x-coordinate of the vertex is going to end up. So the vertex has an x-coordinate h, and then the up or down k is going to end up being the y-coordinate of the vertex. So the vertex, if we're in this form, is hk. The axis of symmetry goes through the vertex, and that's always a vertical line. So you should always say x equals, and then it'll be the x-coordinate of the vertex, so x equals h. And then when I write opening here, I really mean, does this open upward or downward? Well, it's going to open upward if a is positive, because then we don't have a reflection. And then if a is negative, it does have a reflection, and it will open downward. So this decision is, of course, based on the sign of a. So this is our standard form. The other ax squared plus bx plus c is our general form. So here we have an example. This is given in standard form. So with knowing your transformations, that helps you find the vertex, of course. Here we would shift to the left 3, and then it's going to have a stretch of 2 and a reflection, and then down 2. Well, those shifts are going to tell us where the vertex is. So this will be left 3 and down 2. The vertex is going to end up at -3, -2. And once you know the vertex, the axis of symmetry is simply the line that goes through it, the vertical line. So it's x equals -3. All right, well, let's graph it. And I did this without graphing it. You don't have to graph it to understand this, but the graph, of course, might help you. So some of you maybe want to graph it first. So we go to the left 3, and then the 2 would stretch it, but I'm going to handle the 2 and the negative at the same time. So when I go back here, now, my original shifts back. Here's my original. I'll just put it in really light. I don't actually want this on my graph. It shifts back here. Remember the out 1, up 1, out 2, up 4. Now it's going to go out 1, and then instead of down, we're going to go down because of the negative, but instead of down 1, you take 1 times 2, so you go down 2. And then out 2, instead of down 4, you double it. 4 times 2 is 8. So 4, 8. That helps you with the stretch. And then it opens down. Whoops, I'm not done, of course. I still need to shift this down 2. I'll just do this lightly. So here's what I have so far. And then move that down 2. And I'll I'll use a different color if I can find one. This will work. It's kind of thick though. Whoops, I needed to go down 2. And these are here and here. Oh, dang it. I did go down 2 for this one. This one I went down 3 by accident. That's where I messed up. Okay, there we go. So here's f at x equals -2 times x plus 3 squared minus 2. Okay, so there's our vertex. And of course our axis of symmetry goes right through there, so that's why it's x equals -3. But if you understand how to get the vertex here, I would start with that and then use this to do, okay, from there out 1, and then take, instead of down 1, down 2 from there, and just, you know, skip all those extra steps of transforming it. So let's do it that way for the next one. Oops. Sorry, there we go. And we have a lot more questions to answer on this one. We're asked for not just the vertex and axis of symmetry, but all of this other stuff. All right, well, the vertex, so looking here, this is going to go right 2 and down 4. So the vertex is 2, -4. So there we go. Whoops. And because 1/2 is positive, this opens up. Once I get those two things, I'm going to just complete the graph and then use the graph to help me with the rest of the questions. So I go out 1, and instead of up 1, I get, that's multiplied by 1/2. So it's going to be 1/2 as far. And then out 2, the original would go up 4, but again, multiplied by 1/2. And so we're going to get that wider parabola. It looks something like this. And actually we could, if you want to be more accurate, if you go out 3, 3 squared is 9, so 1/2 of 9 would be 4.5 units up. So I'm not being very accurate on this side. Out 3, up 4.5. It's more like this. There we go. That's pretty nice. Okay, and I didn't ask for the axis of symmetry, but of course it's, I'll just write it down here anyway. X equals 2. Then the domain, that's easy for parabolas. It's always all real numbers. You shouldn't even have to think about that one. It's always going to have, you know, you can always square numbers and add and subtract, so always all reals. The range, once you get the graph, you know, and see where the min or max is, that makes it pretty easy to find the range. We can see this has a minimum of -4, and then from there goes on forever to infinity. The max or min, of course you need to identify which one. It's going to be a min. So a minimum of, and the minimum value is not the point, it's the y-coordinate. It's -4. And that occurs at x equals 2. So in other words, when you plug in 2, you get the minimum output of -4. All right, x-intercepts. The graph, now sometimes you won't have any x-intercepts. Like in this previous graph, it opened down and it was already below the x-axis. So there is no x-intercepts for this graph. So pay attention to your graph. You might be able to skip that question. But in this one, of course, we have x-intercepts. So that's when we're going to, I'll do it over here, solve 0 equals 1/2 times x minus 2 squared minus 4. We want to know where x, or what values of x give us the output 0, right? These have a y-coordinate of 0. So you can square this, expand everything, then see if it factors or use the quadratic formula. But if it starts in standard form like this, it's much easier to just say, well, this square is already completed. I'm going to isolate this square. So when I say completed, I mean, remember back in if you remember this, back when you derived the quadratic formula, you had to complete the square, and before you knew the quadratic formula, you had to solve by completing the square. That whole process is basically already done for us, so we don't need to do it. So add the 4. Fortunately, I didn't leave myself a lot of room. I wrote so big here. And then multiply both sides by 2, so we get 8 equals x minus 2 squared. And now take the square root of both sides. So we get plus or minus the square root of 8 equals x minus 2. Don't forget the plus or minus here. There's two values, 2 signs here that you could square and get 8. So there's 2 answers. And then add 2 to both sides. 2 plus or minus. And now the square root of 8, I'm going to simplify that to 2 square root of 2. So these are irrational numbers. You don't want to just guess by looking at the graph. You want to find them algebraically. The x coordinates are 2. The left one is 2 minus the square root of 2, 0. And the right one is 2 plus the square root of 2, 0. Okay, and then we have one more question, and that's the y-intercept. And of course, the y-intercept is where the x-coordinate is 0. We want to find this point here. And we actually already found it because it happened to be when we went out to up 2, we can see it's -2. But if it wasn't clear from the graph what it was, you should find f at 0. You're letting x equal 0. And when you plug 0 in, here you get -2 squared is 4. 4 times a half is 2. 2 minus 4 is our -2. That verifies that our graph is accurate. If you're getting things that aren't working right, like this doesn't agree with your graph, or these intercept values don't agree with your graph, it means you made a mistake somewhere. Everything should jive, if you will, and if they don't, look for a mistake because something is wrong. That's how you catch mistakes. All right, the next one, this one doesn't have a shift up or down, it just shifts left 1 unit. So the vertex is going to be at -1, 0. And then this one will open down because of the negative. And when we graph this, then we're going to go out 1 and then take that times -3. Instead of going down 1, we'll go down 3. So see this one again, we'll get the y-intercept easily. And then when we go out 2, instead of going down 4, we would go down -12, and that's going to be off my grid a little bit here, but so this is -10, 11, let's say this is about -12, so that point is 1, -12. And then, of course, the symmetry, we know this is just straight across over here at -3, -12. So that is a stretch, of course. And our axis of symmetry would be x equals -1. Always state that as a vertical line. Don't forget the x equals. It's not clear what you mean if you just write -1. Okay, what else? Domain, again, that's just always all reals. And then the range, this one has a max. The max value is 0, right, on the x-axis there. So it's -infinity to 0. And like I said, there's a max, so a max of the maximum output is 0, and that occurs at x equals -1. When we plug in -1, we get out 0. X-intercepts, well, from the graph, this is easy. We don't really need to do anything. We can see it's -1, 0. There's only 1 this time. That's the only way you're going to get one x-intercept with a quadratic, is if the vertex itself is on the x-axis. Otherwise, you'll get 0 or 2 depending on the location. I was going to say, and you can verify this algebraically if you let this equal 0 and solve. Right? You can divide by -3, and now you've got this equals 0. Take the square root of both sides, and you'll get x equals -1. Or just use the zero factor property there would work as well. All right, what did I forget? Oh, the y-intercept. Well, we already said that's 0, -3. But you can, again, you can always verify algebraically. When you plug 0 in, you get -3 times 1 is -3. Everything meshes as it should. All right, one more of this type. So another one in standard form. This is going to go right 7 and then up 8. So this is up here. That's our vertex. And it opens upward. So that now we're not going to be any x-intercepts. That'll save us some work. There's no stretch or compression or reflection, so we just would go out 1, up 1. And then out 2, up 4. I'll just kind of estimate. Just our standard shape, same shape as y equals x squared. Okay, again, axis, that's x equals 7, right here. Domain is all reals. Range, you see this one that has the smallest value at 8, and then goes to infinity. And again, the smallest value, so it's a min of 8 at x equals 7. We already mentioned there's no x-intercepts. And then the y-intercept, we can see it's way up high, so it's not clear, so we'll use algebra for sure. We want to find f at 0, which is 0 minus 7 squared plus 8. Well, that's 49 plus 8, which is 57. Seems to agree with our graph that it would be way up there. There's always a y-intercept. The graph is always going to cross the y-axis somewhere. And of course only one, since we have a function. All right, so if it's in standard form, it's really simple to find the vertex and complete the graph and then answer all the questions. So I say always find the vertex first, because that helps you answer all of the other questions, the vertex and the opening. All right, now we're going to talk about, well, what if it's not in that standard form? It's in general form. How am I going to know where this thing is shifting? And so I'm going to show you two ways. And the book focuses on the first way, but that's not the way that I prefer, so that I'm not going to do this more than once. I'm only going to do it once just to show you, and then I'm going to show you the way that I prefer to use. Well, the first thing I want you to notice about the two forms, and they're both written right here, is that there's a reason these are both listed as A, and that's because that's always going to end up being the same number. But of course B and C are not the same as H and K. Okay? So we're going to review completing the square here, and I had already mentioned the completing the square idea. So before I do this problem here, let me just remind you how to complete the square. Let's use the back of this paper. Say we have, so completing the square means you have, basically you want to create a trinomial that you can factor as two perfect squares. So there might be some steps involved to get it to this point, but let me just give an example first. Say it's x squared plus 16x, and you want to know what number should I add here to make this a perfect square so it'll factor in a way that the two binomials I get are exactly the same. And this has to be a 1 here in order to do this. And if that's a 1, then of course this is x and this is x. So whatever you put in here, they need to be the same, and they need to add up to this number. Well, the easiest way to do that, to figure that out is say, well, whatever this is, cut it in half. Then those two things will for sure be the same and add up to this. So it's going to be plus 8 and plus 8 here. Well, then what is this number? It's going to be 8 times 8, or 8 squared, which is, of course, 64, right? Well, if you make this more general, call this a b here, then whatever this number is, again, this is x and x, you're going to cut it in half. So I don't know what half of b is, so I'm just going to represent it algebraically as b over 2. And then this number times this number is what goes here, so it's b over 2 squared. So this is how we complete the square. We're going to use this in this problem, and again, we're going to use it in the circle problems that I kind of tacked on in this section. All right, so let's proceed with this problem now that we know how to complete the square. So this, we're going to start with this. And so we're going to basically try to create this pattern, the x squared plus bx from here. The negative 3 isn't going to be, it's going to be outside of that completing the square process. The problem with this is the 2 makes it so we're not ready to complete the square. So what we're going to do is factor a 2 out of these two terms. And then inside the parentheses, we get x squared plus 3x. This is where we're going to complete the square, inside here. So now we need to, just in here, do what we did when we completed the square over there. Add to this half of this number, which is 3 squared. Now once we add this in here, this becomes not equal to this. So we need to make an adjustment so that if we were going to redistribute and subtract the numbers, we would still end up with this, right? We can't use an equal sign if these aren't actually equal. So keep in mind this here is 9/4, right? I'll write 9/4 here. So what we do is we say, okay, it looks like I added 9/4, but actually I added 2 times 9/4. 2 times 9/4 is 9/2, right? This would cancel with this and we get 9/2. So I added, from the original thing, I added 9/2. How do I balance it out? Well, I would subtract 9/2. And that's a little tricky. That's where it gets kind of tricky and I think confusing for people. So let me rewrite this as 9/4, and then these two things we're going to add, and we want to use fractions. So negative 3 is negative 6/2, and then we'll subtract 9/2. Okay, and now, whoops, I forgot my squared. This is my perfect square that I'm going to factor. Before I do that, though, I just want to you can always check yourself, distribute. This step here is 2x squared plus 6x plus 9/4 times 2 is 18/4, or 9/2, and then minus 15/2, which is 2x squared plus 6x minus, sorry, I was already thinking about this difference of 6. That's 15/2. 9 minus 5 is minus 6/2, which is our negative 3. So it equals the original. That's critical to make sure it equals the original expression, otherwise you don't have the same parabola, okay? And so we've got 2 times x plus 3/2 squared minus 15/2. Now that it's in this form, now it's in the standard form, we can find the vertex, which is from here, this will go left 3/2, and then down 15 halves. The vertex is -3 halves, -15 halves. So notice you would not see that just by looking at A, B, and C, right? So I think most of you would agree that that's not a very fun process. So I'm going to show you a way that I think is easier, and that is to use the vertex formula. So just like when we solve quadratic equations, we can come up with a quadratic formula, which is a shortcut for completing the square. This is the same idea here. Instead of completing the square, since it's the same thing we would, do no matter what, we can just write a formula. No matter what these numbers are, we'd pull this out. So that's when you pull that out, it's taking this divided by this. No, 6 divided by 2 is 3. So that's our b over a. That's that part of the formula. And then from here to get this, you have to divide by 2. That's where the 2 comes from. And so this number in here is the b over 2a, but then the vertex actually ends up at the opposite because the transformations go opposite, so that's why we have the negative. So if we use this formula, the first coordinate here is going to be the x-coordinate of our vertex, and then whatever that number is, we'll just plug it into the function to get the y-coordinate. So we're going to redo this and show we can get the vertex without actually doing all of this. So we start with it was f at x is 2x squared plus 6x minus 3. And using the vertex formula, the h, so this was hk, so we can say, well, h is negative b over 2a, which is negative 6 over 2 times 2, or negative 6/4, which is negative 3 halves. And so see, that's the x-coordinate of the vertex. Then the y-coordinate, this looks kind of messy, I guess, but that just means plug in whatever number you get here, plug it in. So k is f at negative 3 halves. We just plug that into 2x squared plus 6x minus 3, so we've got 2 times negative 3 halves squared plus 6 times negative 3 halves minus 3. So 2 times 9/4. Now this simplifies, but I'm kind of thinking ahead to the fact that this is going to be a half. So I'm going to leave this actually as a half and write it as negative 18 halves, because I'm going to want a common denominator here. And then, and then the minus 3, I'll write that as a half in the next step. So this is 18/4, or 9 halves, right? If we simplify 9 halves, and we've got minus 18 halves, and then minus 3 is minus 6 halves. Got to get better at working, with fractions and being able to find common denominators. You should not be using decimals here or mixed numbers. Use fractions. 9 minus 18 is negative 9, and then negative 9 minus 6 is negative 15. So this is negative 15 halves, which is, of course, the same y-coordinate we had here. So the vertex is negative 3 halves, negative 15 halves. And once we know the vertex, we can take this function, which was in general form, and put it in standard form, because we know in the here, let me write that form down here. In this standard form, the a's are the same. So this 2 would go out front, and then the x minus h is going to be x minus whatever this x-coordinate is, so it becomes x plus 3 halves, and then that's squared, and then plus k, and this is k. So we can, if we find the vertex first, just plug those in to get the standard form, and we don't have to do that completing the square process. Okay, I think that's a good place for me to take a break anyway. Get a drink of water. and then we'll do a couple of problems where, so these are similar to the other problems, but they're in ax squared plus bx plus c form, or general form, and we're not going to complete the square to get it in. It doesn't ask us to put it in standard form, but let's practice it anyway. We won't complete the square, we'll use the vertex formula. We'll do that in the next video.